Next speaker is Lev Vidmar from Joseph Stefan Institute, and he will talk about spectral functions in finite disordered spin chains. Please.
Yeah, okay, thank you. Thank you, the organizers, for giving me this opportunity. So I agree with John that I would be very happy to be in Santa Barbara now, but the situation is as it is. So by the way, can you see my full screen now in the pointer? Does that work okay? Yeah. Okay, so today I will talk about phenomenology of spectral functions in finite spin chains, which are subject to disorder. So this is the work that we did in collaboration with Marcin Marciejewski from Wrocław, who was really the driving force of this project, and then his student Bartosz and Janez Bonča from Ljubljana. And I also acknowledge previous collaboration with my student Jan Šuntas and Tomáš Proseno on topics that are going to be weekly, also related to what I'm gonna talk about today. So this KITP program is about non-equilibrium quantum many-body physics, and as we know, there are different aspects of this topic. So just to summarize a few of them. So there are many people nowadays that are interested in questions like thermalization or absence of thermalization after quantum quenches in isolated quantum systems. On the other hand, many people are focused on the quantum information aspect of this question, or a group of other people are mostly interested in transport properties, whether the system is diffusive but has ballistic transport, or there is no transport at all. And so we as physicists, in particular theoretical physicists, we are interested in identifying common mechanisms behind all these pictures. And one possible answer to this is that, well, if we think about thermalization or scrambling or diffusive transport, then the underlying phenomenon that is responsible for that is what is nowadays called quantum many-body chaos. On the other hand, that, you know, it's a simple expression, but rigorous mathematical definition of that in many-body systems on a lattice is still something that is under consideration. And there are many studies nowadays that try to shed more light, more understanding on this concept. So chaotic behavior or thermalizing behavior is something that's going to be relevant for my talk. On the other hand, there are also many cases where ergodicity is broken. So we are interested in understanding general consequences. Why or when does ergodicity break? And in this sense, I mean, just to give to give some main ideas, the main question that we are interested in is how do counterexamples to thermalization look? So we know at least few cases in quantum many-body physics where thermalization, I mean, or ergodicity is indeed broken, but in the context of parameter space of the Hamiltonian, if we consider, let's say, the G is some tuning parameter, then this is more or less limited to a singular point. On the other hand, what is now interested and highly often debated is whether there exist so-called generic counterexamples to thermalization, and if they do, right, like shown in this picture, so if there is some, let's say, non-zero, finite and non-zero value of the parameter where we see the transition from non-thermal to thermal behavior, then the question is, then one can say whether we actually observe a phase transition between thermalizing and non-thermalizing phases of matter. So these are all questions that are relevant for my talk. I will not directly address these questions. Let me give you a few examples of what I had in mind with ergodicity breaking mechanisms. So one well-known example, which I'm not gonna study in detail in this talk, is the so-called beta-ansatz integrability of clean Heisenberg chains, where we know nowadays for sure that there can be dynamics that is non-ergodic, transport may be ballistic, and observables after quantum quenches are described by the so-called generalized Gibbs ensemble. On the other hand, what is more relevant for my talk today are systems with disorder. So in the first step, I mean, if we have non-interacting system, free fermions subject to disorder, it's well known that disorder may give rise to Anderson insulating state, which is which is in which eigenstates are localized in real space. Now, even more important is what question or more challenging question is what happens when you add interactions to the Anderson insulator. So here, according to some proposals, that may give rise to a new phase of matter that is called many-body localization. Now, if that, according to these suggestions or proposals, then this is indeed a fascinating phenomenon that may give rise to so-called dynamical or entanglement phase transition to an ergodic phase, which actually exhibits some emergent, some nice structure, some emergent integrability. Now, this is the framework that I'm going to focus on in this talk. Now, the purpose of my talk is rather modest. I will not talk now about stability or instability or properties of these transitions. I will focus on one particular aspect of systems which are subject to quench disorder, and this is the so-called anomalous dynamics. Anomalous dynamics observed in quantum systems, mostly quantum spin chains, isolated quantum spin chains, subject to disorder. So there have been many studies about that in the last, let's say, 5-6 years. So few remarkable observations are given here, and there is like more than a complete list of works that study that. So one interesting aspect observed in many studies is that in time domain, when you study non-equilibrium dynamics, people have observed subdiffusive propagation of, let's say, either some initial special from some special initial states. On the other hand, in the frequency domain, it was rather fascinating observation that the spectral function exhibits some, I would say, very atypical, or let's say anomalous 1/omega scaling, which is, as I said, it finds some similar examples in the literature where this is observed. But recently, that has been observed in disordered spin chains, actually in several works. So now, I mean, let me now here express the two main ideas or the two main open questions that I would like to address in this talk, and this is that. So these are these two questions. So the first question is, what do this feature mean? What is the interpretation of this feature? Is this is this a hallmark of some new regime, of some new universal regime that we kind of maybe 10 years ago we have not expected? Is this a signature of a phase transition, or on the other hand, is this effect rather some effect of proximity to some integrable point? And indeed, basically, the discussion that I'm going to have in the following is more along the lines of this second point. Another thing with this aspect that is also very interesting is that what is the relation of all these anomalous dynamics, anomalous, let's say, transport properties with other ergodicity indicators of ergodicity breakdowns. So recently in the literature, there were many studies of many different indicators, and the relationship between all these indicators is I would say far from complete, or far from converged. Now, in this talk, I will talk about spectral functions, which are simply Fourier transforms of the autocorrelation functions. Mostly, I will show numerical results for the integrated spectral functions, which is simply defined here. From time for if in the results we subtract the diagonal parts of the spectral function of the I of omega, then we refer to that as I tilde. This is the regular part. So all this analysis is performed using exact normalization, which enables us to get the matrix elements and the energy eigenstates from energy eigenstates. So okay, so the model that I'm going to study is the random field XXZ Heisenberg chain. It's a well-known model that has these random fields that are independent and identically distributed with this box-like distribution. So W, I'm going to refer to W simply as the disorder, or the amplitude of the disorder. So this is the parameter space that we are exploring. So let me here argue about one thing that may have some consequences for the further discussion. So if this parameters delta, so delta here is really the anisotropy of the Heisenberg chain. So if this delta is, let's say, order 1, and if W is order 1, this is something that we usually in physics would say It's a sweet spot of parameters, indeed, in this sweet spot of parameters, features like eigenstate normalization hypothesis and so on, or other indicators of quantum chaos are usually explored and identified. Right? So all the high accuracy studies of ETH and quantum chaos are typically performed in this sweet spot of parameters. On the other hand, now in these studies of random field disordered spin chains, we typically, I mean, most of us, we crank up parameters like we set W to 3, 5, 4, 5, I mean, to large values, which, you know, maybe very demanding for numerical calculations to give reliable results. So what I want to argue now in the next 20 minutes of 10 minutes of this talk is that many properties in this parameter regime, like the spectral functions of observables that I'm going to study, are actually dominated, or let's say governed or influenced by the physics in this delta 0 point. So delta 0 point in this parameter is simply we could call it non-interacting Hamiltonian, or the Hamiltonian that can be mapped to free fermions with disorder. This is simply the Anderson insulator. So in the Anderson insulator, as we know, we have localized, we can call this system as an integrable system. It has Anderson local integrals of motions that I will denote as Q alpha. These are single particle eigenstates of the Anderson Hamiltonian. So let me go now to some specific results that I'm going to present to you. So these are the results for the integrated spectral function for spin imbalance. So the observable that we study here is spin imbalance, which is an extensive observable. So it's a linear superposition of local SZ operators. So it is self-averaging, and this is convenient for the numerical analysis, also to reduce finite size effects. Now here in this figure, there are two types of results. So the first type, the first set of results are results which are shown as lines. So these lines here are results for the Anderson insulator, or delta 0 in the XXZ Hamiltonian. So the remarkable feature is here is that this integrated spectral function is essentially flat at low omega, and then it increases at higher omega. So in this talk, I will not be interested in the high omega, in the large omega regime. So everything omega larger than 1, I'm not interested in at this point. So the regimes of frequencies I'm interested in is 10 to minus 3, 10 to minus 2, 10 to minus 1, and so on. So the main message here is that if delta is 0, so in the Anderson insulator, the integrated spectral function is a constant, which means that then the true spectral function is basically the delta function, at least in the low omega regime. Now, to be even more precise, I mean, it is correct to say that this is a delta function, but the weight of the delta function, or if you wish to call it the Drude weight, can be decomposed into several contributions, and all these contributions come from the projection of the observable to the Anderson Lyons Q alpha, and the observable is such that actually it has non-vanishing projections on many Anderson Lyons. Now, on the other hand, what is our goal to describe, what is challenging to be described, are the results for the interacting system. So with symbols here, I show results for the interacting system, and so this is what, you know, referring back to one of my previous slides, this is what we could call anomalous behavior or anomalous dynamics. And from now on, I will focus on a phenomenological framework to quantitatively describe this behavior. Okay, so for the phenomenological description of this of those interacting systems, there are two steps that are important, and let me now clarify which two steps are here crucial. So the first step that is important is that when we start from the non-interacting case, delta 0, we have the delta functions, and then as a consequence of interaction, we allow for the Anderson Lyons to delocalize, or to acquire a finite, let's say, finite relaxation time that we here denote as tau alpha. So an important step here is that since this is a sum which stems from different contributions of different overlaps of observable with different Anderson-Lyons, as a consequence of interaction, we still have the sum, which means that we model the delta function by the Lorentzian. So the delta function is broadened to the Lorentzian. But the point here is that it's not only one Lorentzian that is relevant, but it's a superposition of several Lorentzians and that have the width determined by this tau alpha, the relaxation times of Anderson-Lyons. And of course, I mean, if these tau alphas are all the same, we don't need the sum. But what I want to argue here at this point is that this is indeed, I mean, the distributions of this tau alpha may be indeed non-sharp, or they may be indeed very broad. And this is the idea of the main essence of the next step, which refers to establishing actually the distribution of these relaxation times, right? And we calculated down recently that numerically in a given model, and we observed that actually to very good approximation, this distribution of relaxation times is indeed very well described by the power law, with the exponent mu. Of course, this power law cannot extend forever. It's a power law in a given interval spanned from some, let's say, tau min to tau max. So tau min then means this is the shortest relaxation time of Anderson-Lyons in an interacting system, while tau max is the longest relaxation time of Anderson-Lyons in the interacting system. And I'm going to refer to tau min and tau max in the next slides. So now, if we insert now this distribution to this equation and replace the sum by the integral, then we get this expression. We get this then theoretical phenomenological framework to describe the spectral function, which is given by this integral. Of course, there is another assumption that I have not discussed in details, but we also check that numerically, and this is that the alphas are essentially uncorrelated with tau alpha, so we just replace the alpha by some average value. But this is, I would say, still rather simple model to describe observables, which of course has some unknown parameters in principle, which are tau min, tau max, and this mu. But as I'm going to show in the following 5 minutes, that actually describes excellently the actual numerical results. Now, before I go to the details, to the detailed numerical comparison to this phenomenological model, let me first argue about two generic properties of this description. So, of course, this description is relevant if this tau max and tau min are very different, right? So, in other words, if this tau max is orders of magnitude larger than tau min, it doesn't mean that if tau max and tau min are the same or of the same order that the description breaks down. It doesn't break down. It's just that it can be simplified, right? We don't need that then several. We don't need the whole distribution. We can just describe it by a single Lorentzian. Now, coming back to these parameter regimes that I have discussed, indeed, I mean, if we are, let's say, in the regime where all the parameters are of the same order, right? That is the result shown here. Basically, we have the integrated spectral function, which is just a line. So if the integrated spectral function is a line, it means that the actual spectral function is flat, it's a constant, and this is consistent with diffusion. This is consistent with diffusive transport and ergodicity, thermalization, and so on. Now, on the other hand, what is also interesting here is that when we increase this order, but actually not much, this linear regime in the integrated spectral function shifts to lower frequencies, right? And then what we actually do describe by this model is then this regime between the inverse of tau min and the inverse of tau max, right? So the larger the disorder, the larger the span from this minimal to maximal omega, and this is the regime that we are actually describing. Now, on the other hand, very instructive is this case mu equal 1, in which a closed form analytical expression can be obtained. And in this case, the result is rather simple and remarkable. And here one can actually simply show that this is the 1 over omega behavior, as has been observed actually in several previous studies. Now, in general, if mu is not exactly 1, so at this point, I don't have any strong theoretical argument that this mu should be 1, right? It's just more like a numerical observation. But even if mu is not 1, right? One can say roughly that the spectral function scales as 1 over omega to some power eta, where eta is something between 0 and 2. Right. Okay, so for the last, let's say 3-4 minutes, let me show you the actual numerical results. So these are the numerical results first for the integrated spectral functions, which are averaged over different disorder realizations for the disorders spanning from 1 to 6, and we see that essentially for a wide range of disorders, we can describe the numerical results very accurately. So here the points are the numerical results, and the lines are obtained by integrating these models and fitting the tau max, tau min, and mu to the data. Now, so one important message is that indeed this model, this phenomenological description can very accurately describe the actual numerical data. That's the first main result. Now, the second main result, which is also pretty remarkable, is that then one can extract these parameters from the best fits, right? And then study the behavior of these parameters as a function, let's say, when the disorder is increased. And this, so for clarity, I would just show you here results for tau max. So tau max, again, is the longest relaxation time of Anderson-Lyons, which increases as a function of the disorder. Now, if one rescales tau max by the Heisenberg time, right, which Heisenberg time is the inverse of the mean level spacing, then one sees that actually very soon, like already at W2, around 2, for the system sizes available or that can be treated by exact diagonalization, we see that the largest relaxation time becomes larger than the Heisenberg time. Okay, and very similar results actually occur if we fit individual disorder realization. So that is the advantage of this approach, because we can perform a fit for individual disorder realization, and then do it like, I don't know, 1,000 times, and then study the distributions of parameters, of the optimal parameters obtained in this way. So these are the cumulant distribution functions from the longest relaxation tau max. And again, very consistently with previous results, around W2 or 2.2, we see that the majority of samples, the longest relaxation time tau max exceeds this disorder, let's say crossing point, which is around W2. Now, let me now finish this talk by giving you some interpretation of these results. So what have we learned from this analysis? So the first outcome the first result is very simple, and this is that we interpret anomalous dynamics as the dynamics that arises from the fact that certain Anderson-Lyons acquire finite relaxation times in the systems under investigation. Now, another more quantitative question is what is the distribution of this relaxation time? So if one studies the whole distribution of relaxation time, one sees that there is this, I may call it a crossing point, below which all Anderson-Lyons are delocalized in the system. But if the disorder is larger, then effectively we see coexistence of two types of Lyons, those for which the relaxation time is larger than the Heisenberg time, and those for which relaxation time is shorter than Heisenberg time. So in the first case, effectively for a given finite system, it appears as if these Lyons are truly conserved. So they are the true Lyons. On the other hand, in this case, they are not conserved because of the presence of interactions. Now to conclude my talk, let me again show you this sketch. So what I want to argue is that on the one hand, by describing quantitatively the spectral functions with our phenomenological framework, we could get insight about this crossing regime on which the longest relaxation time of Anderson-Lyon crosses or reaches the Heisenberg time. On the other hand, if one compares now quantitatively these values to other values from the literature, we see that many other ergodicity indicators indicate similar features of ergodicity breakdown exact or almost exactly at the same point. So this is the case for the so-called tauless time reaching Heisenberg time that one can study from the spectral form factor, or the level spacing ratio or entanglement entropy departing from random matrix theory predictions or the fidelity, susceptibility being maximal, and so on. So all this here we are collecting many different indicators that actually at the end of the day, I mean, when quantitatively analyzed, show a very consistent picture of some, let's say, crossing scale that emerges, that is, I would say, rather low, but that actually plays very important role in analyzing the response in finite disorder spin chains. And with this, I would like to thank for your attention.
Thank you very much, Lev. I'll just call for questions and comments. Seems to be. I don't see any hands there. Okay, let me start very innocently. So what are the experimental systems that you would be able to investigate on this?
Yeah, the experimental systems, well, experimental systems are well, yeah. So the 1D spin chains are the ones that are here to target, and they are not far from things that can be realized using ultra cold atoms. Now, the interesting question that persists here for further studies is how this is manifested in let's say Hubbard-like systems, right? Two-component systems that are then even closer to experimental implementation. And I would say that the mechanism or the framework that we here are introducing, so I would say it's pretty generic and robust enough to be relevant also for two-component systems.
Thanks. Okay, so there's a question by Philip Crowley.
Sorry, I just had to mute myself. Hey, thanks for the talk. Did you look at models which didn't have a kind of neighboring free fermion picture? And how would you expect, basically, how would you expect any of the pictures to change if I wasn't choosing a model of MBL which was like neighboring to an Anderson insulator?
Yeah, that's a good point. I mean, we haven't yet done that. So yeah, so there, yeah, so clearly this framework relies on having some reference integrable point. I mean, whether this is like truly free fermion or something else, I wouldn't say. Then I consider that as a quantitative question. How do then particular integrals of motion relax, or how would they relax? How would they behave? I would say this is a generic picture, but as I said, it should be tested to proximity to different sorts of integrable points.
Okay, so you're saying that it's not so much that they're the Anderson insulator LIOMs that you're interested in, but just that there's like some strong disordered limit with LIOMs. Yeah.
So you see, the point is the following, right? The key point is here that you need this. So in terms of the non-interacting limit, or let's say in the integrable point, what is needed for the integrable point is that actually here in the spectral function you have this flat regime, so basically a gap. It's not entirely flat, but to very high precision there is almost no spectral weight here. So that is the point. I mean, you need that. If we have the reference integrable point that exhibits this feature, then you can apply this idea in the sense that you broaden the delta functions by some Lorentzian.
Okay. Thank you.
Thanks. There's still a question by Anatoly.
Hi, Lev. For the talk. I have a question. We were kind of trying to make sense of all your results and our results, and just want to check like what you think about maybe qualitative picture. So suppose we just imagine we can go to thermodynamic limit. Though I can imagine like maybe interpretation of your data is the following. So you locally have Fermi golden rule rate, right? But this function f of omega becomes like very rough as you increase this order. So it means like locally it just sort of fluctuates a lot. So sometimes you have more states, sometimes you don't have states. So it's a continuous on the level spacing. Well, there are no level spacing, thermodynamic limit, but it becomes like more and more rough. So in this sense, like I have a question. Did you try maybe to think like if you increase W, what changes mu, tau mean, tau max, they change together? Like, do you have any idea?
Yeah, we thought about that. So you see, so the main statement is so these are the results for tau max and mu that we obtained from that analysis. I haven't really mentioned that in my talk. Yeah. So what happens? So now, okay. So of course, yeah, I agree. The most interesting regime is then when you further increase this order, and then you ask, I mean, at which point does it eventually break down, right? So of course, what happens is that if tau max increases beyond Heisenberg time, it means that the inverse tau max goes here to smaller and smaller and smaller omega, right? So essentially, if you had larger systems, right, this was then this anomalous part of the spectral function would just increase. So this means that effectively, with a given finite system, we are just feeding a small part of this anomalous behavior, and as a consequence, the quantitative values of these parameters, like mu, are less and less, I would say, sharply defined. Right. That's one consequence. Now, here by analyzing the distributions of this parameter mu, we see very much that actually it's centered around 1, unless disorders are so large, like here, I don't know, 5 or 4 or 5 or even more, right? That the fitting becomes less and less reliable. So I would say the main message is that as long as you see this anomalous low frequency dynamics, it means that the relaxation times, the shortest and the longest, are extremely broad, but they exist. I mean, the shortest relaxation time does not diverge, right? We never see that the shortest relaxation times diverge. We never see that all Anderson lines become localized. That is not the case as long as you have here some low frequency dynamics. Now, to settle on the quantitative value of that is a harder question. I would say that it's not unexpected that this mu eventually remains close to 1 for all disorders.
Mm-hmm. Okay, thank you. I think we need to move forward now. So okay. Thank you once more, Lev.